We typically look at the Great Pyramid as an architectural monument, but its physical reality is simpler. It is a 6 million ton static mass of dense limestone. Geologically, this mass sits directly over the Mokattam Limestone Formation, an active, saturated aquifer filled with subterranean water. Placing a structure this scale onto that bedrock creates significant downward force, designed to interact with the fluid system trapped beneath it. The underlying mechanical principle is quite straightforward. Increasing the load on a pressurized system forces the internal pressure to rise. This weight physically compresses the rock matrix, displacing the trapped water and forcing it upward through the bedrock toward the surface. If correct, the layout of the Giza Plateau was determined by hydrogeology rather than symbolic placement. Inside the structure, the standard hallmarks of Egyptian funerary culture are missing. There are zero texts, hieroglyphs, or murals, only heavy-duty, unadorned granite walls and a plain stone box. These internal features appear designed for durability and mechanical function within the core of the mass. On the exterior, the massive causeways are precisely graded and stone-roofed, creating a continuous path leading downhill away from the pyramid's base. While often described as ceremonial, their physical construction is identical to gravity-fed industrial aqueducts. They were built to capture the pressurized fluid as it breached the surface, routing it safely down to municipal hubs in the floodplain. To prove this mechanism actually worked, we must apply standard geotechnical math to the structure's dimensions to see if it generates a functional flow. Our calculation starts with the primary structural inputs, a total mass of 5.9 billion kilograms resting on a base area of 53,060 square meters. This load sits on the Mokattam limestone substrate. This bedrock has a porosity between 15 and 25%, meaning up to a quarter of its volume is empty void space filled with water. That porosity makes the rock function like a rigid sponge, capable of physical compression under an extreme load. Across the pyramid's footprint, the mass generates an applied localized pressure of 1.09 megapascals. This pressure is the engine required to perturb the equilibrium of the aquifer. To find the output, we apply a variable called specific storage, which for this site is 1.844 times 10 to the negative sixth. This value determines the physical limit of the matrix, exactly how much water the rock will expel when it is squeezed. The rock will only yield water as long as that compression is active. It is a finite physical reaction. The interaction between this applied pressure and the bedrock's storativity creates what is known as a hydraulic head. In the case of the Great Pyramid, the calculated hydraulic head is 111.2 meters. A 111-meter head provides the vertical lift needed to force subterranean water out of the ground and into the catchment aqueducts. If the pressure is this high, we have to ask why the water doesn't simply erupt from the ground all at once. The dense rock matrix acts as a natural restrictor, and its permeability determines the speed of the output. By applying a hydraulic conductivity of 1.844 times 10 to the negative 14th meters per second, we can calculate the flow rate using Darcy's law. The result is a continuous, controlled baseline flow of 5.44 times 10 to the negative 9th cubic meters per second. Dividing the total volume of water the rock can expel by this flow rate tells us the operational lifespan of the system. Before the pressure equalizes and the flow stops, the Great Pyramid can operate for 1,268 years. Khufu's 5.9 million-ton mass produces the precise hydraulic head required to maintain this continuous flow for over a millennium. Once the rock matrix consolidates and the pressure equalizes, the water stops moving. This physical limitation explains the historical timeline of the plateau. When Khufu equalized, the builders relocated along the same aquifer to tap a fresh pressure zone. They built the next massive weight, Khafre, to start the hydrostatic process over again. The Sphinx was integrated into this system at its lowest point, where the weathered enclosure sides show its role as a deep catchment basin. The Giza Plateau isn't a collection of pharaonic monuments. It is a sequential record of a civilization depleting a hydrostatic resource. If this hydrostatic model is correct, we should find it applied at other megalithic sites worldwide. The Global Megalithic Hydrogeological Database tracks over 130 sites, comparing regional bedrock, porosity, and structural mass. The data reveals a universal pattern. Immense structural weight is consistently paired with specific hydrogeological substrates. Builders specifically targeted permeable substrates like porous limestone, fractured granite, and chalk. Stonehenge sits over a Cretaceous chalk aquifer with a porosity between 35 and 45%, perfectly suited for this mechanism. Nearly all of these 130 sites are positioned directly over shallow water tables or perched aquifers. The ultimate conclusion is that global site selection was strictly governed by the geotechnical requirements needed to force subterranean water to the surface. Any pressurized system needs an output grid to capture and route the fluid it produces. The database confirms that almost every site on the list features integrated catchment and routing structures. In Egypt, the Osirion was built specifically to interact with the water table, with its massive chambers permanently submerged. The Pyramid of the Sun in Teotihuacan was built directly over a fluid-bearing lava tube with an engineered drainage system. At Machu Picchu, engineered stone-lined channels were built to output water directly from the compressed granite aquifer beneath the site. Across the globe, immense causeways, deep rock-cut cisterns, and heavy stone moats provided the universal infrastructure needed for these massive hydrostatic pumps. The math and the global database suggest that ancient megaliths were built as functional, heavy-duty components, part of a worldwide infrastructure designed to extract work directly from the immense hydrostatic pressure of the Earth.